This video is about force. What are Newton's laws of motion and how can we apply them? We'll also be talking about inertia and equilibrium. You can find information on this for quiz 4B, forces. A force is a push or a pull, and it's also a vector, which means it has direction. We often picture forces by using a free body diagram. Free body diagram is a diagram that shows only a single object but depicts all of the external forces that are acting on that single object. We use the word external because the forces have to come from outside of the object that you are drawing. Let's do a couple examples. Draw the free body diagram of this park bench. Okay, so here we see a park bench with this couple sitting on it, and it's sitting in the park on some, like a sidewalk or some cement. So you want to start by drawing the object itself, the park bench. Just do a rough sketch of a park bench right here. Okay, and there's the arms and the feet. Okay, so there's the object and it's by itself. It's still sitting on the ground, and there's still two people sitting on the bench. But we only draw one object, the bench itself. And as I said in class, you always want to think your forces, it's easier to think your forces as contact forces and field forces. So first, the field force on the bench of gravity. So I'll do this, and that will be the weight of the bench itself. Okay, and that's the only field force we're interested in. There's no magnetic or electric field forces involved here. Everything else is going to be contact forces. So any other arrow I draw in here, it's got to be something in contact with the bench. And so I see here the man's in contact with the bench. The force of the man sitting on the bench is going to pull down on the bench. So this will be the force of the man. Also in contact with the bench is the woman. So we'll put that force also. Also in contact with the bench is, well, you see these are all down. The gravities of the weight of the bench is pulling it down. The man's pushing down on the bench and the woman's pushing down the bench. But the bench is also sitting on the ground, but the ground is pushing up on the bench like this. And we'll talk about why that has to be equal later. There you have it. All the forces that we're interested in are up and down, and we have the force of the ground contacting up, the force of the man, the force of the woman contacting and pushing down, and then the weight of the bench pulling the bench down itself. I'm going to try to draw the arrows to scale, meaning the bigger the arrow, the more force. All right, for our next example, draw the free body diagram of a book that's sliding along a table after it's been pushed. And then it says friction is slowing the book down. So here's our picture, and it's showing this hand is pushing the book and getting it moving, but we're interested in the free body diagram right there after the hand is no longer in contact with the book. The hand is not contacting the book in our diagram. First, I'll start with a picture of the book, and it looks like the book's that with pages in it. And there's our book. And just like before, the book has some weight. So the force of gravity, the weight of the book is pulling it down. That's it for the field forces. Now contact forces. Well, the table is going to be pushing upwards on the book, holding the book up. And those are in balance. Now the book is moving to the right, but it's slowing down because friction is slowing the book down, and so friction is going to have to push backwards to try to slow it down. So friction will be pushing this way on the book, and that's going to be a contact force. So there you have it, and you can kind of see up and down the forces are in balance, so the book doesn't move up and down, and then friction's pushing to the left. So even though the book is moving to the right, the friction is dragging it to the left, trying to slow it down. So those are two examples of free body diagrams. Now what can we do with these? Well, let's talk about net force. The word net is just a way of saying the total force or the sum. The net force is the sum of all the external forces that are acting on an object. We write that in a way that looks confusing at first, but it's this crazy symbol right here. Right there, that is a Greek symbol. It is a Greek sigma, which is a capital S for sum. Whenever you see this symbol in math or in science, it almost always means add up. So it just literally means the sum of the forces. Add up the forces. So let's do a couple examples of adding up the forces. Here I just have some generic object sum box, and it's got 3 forces on it: force 1, force 3, and force 5. So we want to add up the forces. So the equation will look like this: add up the forces. So I'm looking on here and I see 3 forces, and so basically it's going to be force 1 plus force 3 plus force 5. So this just means add up the 3 forces. But when we actually put the numbers in, we have to take into account the directions of the forces. So let me start with force. Well, force 1 is to the left, so it's -2 newtons. And then I'm going to add force 3. Force 3 is pointing right, so that's positive. And then force 5 is pointing right also, so that's positive. So when I add them together, I end up with 3 newtons. And it's positive. The net force is 3 newtons, which means the pink and orange forces to the right are more than the blue force to the left. So when I add it all together, it's like a tug of war, and the ones pulling to the right, the positive direction, wins by 3 newtons. Now in this example, we've got forces in both directions. We do the same thing you do in your math classes. You know, you have the x-axis and the y-axis. You can do this in the z-axis also. But so when we add up our forces, because these are perpendicular, we add them in 2 different directions. So this actually looks like this: sum of the forces in the x direction, that will be this way horizontally, and we have sum of the forces in the y direction, that would be up and down vertically in the y direction. So I do these just like before, but now I have x and y direction. They're separate. They don't affect each other. So in the x direction, again, I have force 3, and I'm adding it to force 1. They're both in the x direction. Okay? And so I have force 3 is -3 newtons. -3 newtons. And then force 1 is positive 2 newtons. So -3 plus 2 gives me a -1 newton. That's the net force in the x direction. Now in the y direction, up and down vertically, it's just equal to force 5, which is up 2 newtons. So in the y direction. And there you have it. The sum of the force in the x direction is -1 newton, because the pink wins by 1 newton, and the sum of the forces in the y direction is positive 2 newtons up. So this brings us to equilibrium. Equilibrium is when the net force is 0. So basically, when all the forces cancel out, we're in equilibrium. When you add up the forces and they add up to 0, they're in equilibrium. So using this example, well, first let's look vertically. Up and down, the net force in the y direction equals 2 newtons up, positive 2 newtons. So it's not in equilibrium up and down. To make it equilibrium up and down, I need to add another force downwards, like this, to balance force 5. And we'll just call that force 4. And that one's going to have to be 2 newtons also. So 2 newtons minus 2 newtons equals 0 newtons. So now we're in equilibrium vertically. Let's look horizontally. Net force in the x direction is going to equal -3 newtons plus 2 newtons. And that's going to be a -1 newton. So we're not in equilibrium. It's not 0 yet. So we're going to have to add another force here. And we'll call that force 2. And I'm looking, I see, since this is 3 and that is 2, this one's got to be 1 newton. Okay, so I just added 1 newton. And now it equals 0 newtons. All right, so now we have an object that's in equilibrium. Up and down, the forces are balanced. Left and right, the forces are balanced, so the net force is 0. So now let's talk about Newton's first law. And usually when people hear Newton's first law, it's pretty long, and there's lots of parts to it. But let me show you the briefest, shortest wording we can have for Newton's first law. It really comes down to this. When an object is in equilibrium, its velocity remains constant, period. You see, you really have to know what equilibrium means. You have to know, and you have to know what it means for velocity to remain constant for this to work. Now let me show you how you can use this statement to explain Newton's first law compared to the typical way of explaining Newton's first law. There's basically two parts of Newton's first law, and let's look at the more obvious one first. Here's typically how you might see Newton's first law, the first part explained. An object at rest remains at rest unless acted on by a net external force. So here's our picture we had earlier of the bench, the park bench, and obviously it's at rest. And if you remember, we had our free body diagram look like this. So you can see that the object is at rest, and it's going to remain at rest because these forces, the net external force is 0. So let's just replace this with my one statement. When an object is in equilibrium, its velocity remains constant. Well, if it's at rest, its velocity is 0. And if it stays at rest, it's staying 0. So you can see how this statement covers this case. As long as it's in equilibrium, then the velocity is constant. And specifically in this case, the velocity is 0. So this is the case where everyone, it's kind of a no-brainer. Now let's try the second part of Newton's first law. And here is how it's usually stated. An object in motion remains in motion with a constant speed in a straight line unless acted on by a net external force. So here we have the book sliding across the table, and here's our free body diagram. And you can see that in our picture, this object's going to remain in motion with constant speed unless there's a net external force. And we can see a net external force. Friction is the extra force pushing back. So that means it's not going to have a constant speed. It's going to be, the book's going to be slowing down. So let's again replace this with the same statement I had before. When an object is in equilibrium, its velocity remains constant. Well, looking at this book as it's sliding across the desk, it is not in equilibrium, so its velocity will not remain constant. So you can see, you can replace that long statement of Newton's first law with just this one. It works in both cases, the same statement. The trick is you have to know what a velocity being constant means, because you can apply it to all sorts of situations. Remember from earlier, if an object is speeding up, its velocity is not constant. If an object is slowing down, its velocity is not constant. Also, the tricky one is when it's turning. As long as it's turning, if it's turning, the velocity is not constant because it's changing direction. You can think of Newton's first law in this more simplified way. When an object is in equilibrium, as long as all the forces cancel out, then the velocity is constant and none of this can happen. If it's not in equilibrium, then one of these three things must be happening to the object. It either has to be speeding up, or it has to be slowing down, or it has to be turning. That's Newton's first law. Newton's first law is also referred to as the law of inertia. And what's inertia? You can think of it two ways. First of all, inertia is basically the object's mass. We measure the mass. We use little lowercase m for mass. We measure in kilograms or grams. That's how you measure inertia. The definition, actually, inertia is a measure of how much the object resists a change in state of motion. Newton's first law is actually called the law of inertia because inertia, you can think of inertia as how well it measures or determines how much an object is going to not keep doing what it's already doing. Here's an example of two objects that have very different inertia. A truck versus motorcycle. The truck has lots of kilograms of mass. The motorcycle has less kilograms of mass. The truck has lots of inertia. The motorcycle has a lower amount of inertia. The truck, if a truck is at rest, it's harder to get the truck moving if it's at rest. If the motorcycle's at rest, it's easier to get the motorcycle to get moving. You could push a motorcycle, but a truck, you probably need some help to push it. And then conversely, if the truck is moving, if this truck is coming towards you, it's going to be harder to stop the truck. The motorcycle is going to be easier to stop. Again, the truck is going to be harder to turn, and the motorcycle is going to be easier to turn. Inertia, the law of inertia. Newton's second law. The acceleration of an object doubles when you double the net force. It also triples when you triple the net force. And is cut in half when you double the inertia or the mass. Newton put it in terms of this acceleration. If you want to accelerate an object, think of a fraction, okay? And remember, things on top of the fraction, whatever you put up here makes acceleration increase or should help acceleration. And then on the bottom of the fraction, if you put something on the bottom of the fraction, when this gets bigger, it makes the fraction smaller. It's going to decrease acceleration. What Newton realized was there's something that makes acceleration happen, and that's called force. You add up the forces on an object, it'll make the object accelerate. Doubling the force will double the acceleration. But he also realized there's something that makes it hard to accelerate an object. And if you remember, what resists an acceleration or resists a change in velocity? It is the inertia, the mass of the object. So this is Newton's second law. Acceleration is the force divided by the mass. Another way you'll see it written is force equals ma. So let's try one example calculation with Newton's second law. Going back to our book being pushed. A student applies a horizontal force of 4 newtons to a 500 gram 0.5 kilogram book to start it sliding across a table against a friction of 1.5 newtons. What is the acceleration of the book while the student is pushing it? Okay, so this is a little bit different than our previous example because it says while the student is actually pushing it. So we need to get our free body diagram first. So here's our free body diagram from before, but this was as the book was sliding across the table after the student pushed it. But this is while the student is pushing it. So it's going to be when the hand is in contact with the book. So we have to add one more force, the force of the student pushing, and the student's going to push the book to the right. So when I add the force of the student, I made it longer because you can look up here and see what the forces are. Let's put our numbers in there. Okay, so this is the force. Okay, the force of friction is 1.5 newtons. And the force of the student is 4 newtons. I don't think we really care about the up and down forces because they're in balance. They're going to cancel each other out, and they're not going to do anything to the motion of the book. It's all about left and right. The forces in the x direction. So adding up the forces in the x direction, we get the forces equal the force of friction plus the force of the student, because they're both in the x direction. And then we're going to add them together, and I get, well, the force of the friction is negative 1.5 newtons, and the force of the student is positive 4 newtons. So I get a net force of 4 minus 1.5, and that equals a positive 2.5 newtons. All right, so that's the net force, but I need to find the acceleration. Acceleration equals the fraction. Let's see, what makes acceleration happen? The force makes it happen, that goes on top, and then what resists acceleration goes on the bottom. That's the inertia or the mass. So now I plug in my numbers. The net force was 2.5 newtons. Okay, and I'm dividing by the mass of the book in kilograms. 0.5 kilograms. And I think you'll find out that half goes into 2.5 5 times. So it's 5 acceleration meters per second squared. And that's the acceleration of the book. It's going to accelerate positive to the right because the student's pushing more than friction. which is a good thing because the student had to push at least 1.5 newtons to get the book to keep it moving. And once he started pushing more than 1.5 newtons, now the book can start accelerating. All right, finally, Newton's third law. When there is a force on one object, there must be an equal and opposite force on another object. Let me just sort of show you with two examples, and both of them will be a little bit silly, I think. Let's think about if you had a hand. Okay, here's my outstretched hand, and you happen to be holding, I don't know, a bird. Let's just try put a little bird in your hand. Okay, there's a bird in the hand. Now, if we're looking at the forces, the bird feels the hand pushing up on the bird. Okay, and we call that's the force of the hand pushing on the bird. The bird feels the force of the hand pushing up on it. Now, Newton's third law says as soon as you have the force of the hand pushing up on the bird, you need an equal and opposite. See, I drew this equal length and opposite direction. You need an equal and opposite force pushing down on the hand. This is the force of the bird pushing down on the hand. So the hand feels the bird pushing on it, and the bird feels the hand pushing on it. These two forces are going to be equal and opposite. As soon as one force happens, the other force has to happen as well. That's Newton's third. So what's kind of amazing about this, let me show you an extreme case where students might get confused about not understanding exactly what the meaning of Newton's third law is. Let's say, for example, that we have a truck, pickup truck driving along like this, okay? And it's driving along, see, it's coming along, and it's driving along, it's like cruising along on the freeway like 60 miles an hour. Now we're also going to have, let's say there's, I don't know, little bugs. And this bug is just flying, trying to cross the street like this. Okay, so here comes a bug trying to cross the street like this, and here comes the truck. Smack! So here's what happens. As soon as the bug contacts the truck, the bug gets squashed, of course, okay? It just becomes a splat on the windshield. And nothing happens to the truck. And what students think when they try to explain this, here's what they think happens, which is wrong. This is going to be incorrect. This is a non-example. This is not what happens. But students think, because the bug got squashed, the force on the bug was huge. Okay, they want to think, if you were to ask them, they would say the force of the car was huge and the force of the bug was tiny. But this is incorrect. This is not correct. See, people think the reason the bug gets squashed is because this truck made a huge force on that little bug and squashed the bug. But that's not what. So let's redo this. The force of the truck on the bug is going to be something like that. Okay. And then equal and opposite is going to be the force of the bug on the truck. All right. I wrote car, but you get the idea. Newton's third law says these forces have to be equal and opposite. It happens all the time. The truck hits the bug, splat, with the same force that the bug hits the truck, splat. The thing is, there's two things going on here. First of all, a bug is not built as strongly as a windshield. Okay, if a windshield and a bug hit, the same amount of force on a bug will splat the bug compared to the amount of force on the windshield. It won't do anything to the windshield. Also, the truck has a big mass compared to the bug has a little tiny mass. Okay, so when we're talking about the accelerations of objects, for example, let's say the acceleration of the truck equals the force of the bug divided by the mass of the truck. Okay, and that's going to make sort of a small acceleration like this. because the mass is huge compared to the force. Now, if we try to figure out the acceleration of the bug, okay, we put the force of the car on top. Remember, these two forces are the same as each other. They're equal and opposites. But the difference here is that the bug has a little tiny mass. All right? So when you take the same force and divide by little tiny mass, what happens is you get a big number. Okay? So the acceleration of the bug is huge compared to the acceleration of the car. Not because the forces are different, but because the masses are different. So the same amount of force, equal and opposite forces, squashes the bug and accelerates the bug backwards, while it does nothing to the windshield and causes the truck to accelerate not at all, hardly at all. That's what it means for Newton's third law. Equal and opposite forces always.